And so essentially here's the nozzle we used. So the point of a nozzle is to do what's called the choked flow, right? You're trying to, by changing the geometry of the flow, you make it go faster or slower. It's the same thing when you have a hose and you put your thumb over it. You know how it comes out faster? It's because, you know, you're reducing the area, so the velocity has to increase. There's a whole equation for it. Anyways, so basically, we're putting this inside a chamber where it's like vacuum. So it's very close to like no pressure. So it's like space more or less. And this plate is at a maximum of like an inch and a quarter away from the nozzle. So inch and a quarter is like this much, not that much, not even. By the time the air leaves this nozzle, it's going about Mach 1, which is the speed of sound. Over the course of an inch and a quarter, it's going Mach 5. It accelerates to Mach 5, which is like 5 times the speed of sound, which is like ridiculously fast. And so essentially what happens is when you blast these plates, you have these things that start to form. These like black lines. It's better visualized on the computer there. Basically what those black lines are is that they're called shock lines, right? So it's like you have this shock, and so it's almost like you take a hose and you're blasting the ground. You know how the water is going to go like whoosh everywhere? That's more or less like what's happening on this plate. But one of the really cool things that we were able to capture, this is kind of what I was telling you before, how it's like, it's something they don't know how to explain, is if you look here, this plate's at like a 22.5 degree angle. So we're shooting it. So you have this flow bouncing off of it, right? But if you look really, really closely, you can see like right here, there's like a little crest. It's a little crest, and we really don't know why it's doing that, but we were able to capture that, which is kind of cool. But for perspective, this is what the project was supposed to look like. This is actually what it did look like. It was built and it was ready to go. But then they told us, as a lab, like, hey, that thing's not going to fit in there because we're not taking out our big thing anymore. So essentially what we did was we just cut it here, which is now basically just this. And then we had to basically machine some things to be able to turn this thing upside down. So although these images look like this, in reality, we flipped it. Yeah, we flipped it. So instead of, here was a motor, we were going to use the plate. We were going to move the plate up and down with that motor. But now instead, this thing was just sitting stationary, hanging upside down. But we still needed to do that distance separation thing. So instead, we used this. So basically, here's the nozzle we used, and we're able to attach the nozzle to like right here, like this, and then using this motor, we're able to essentially raise the nozzle up and down. And when you raise the nozzle, you're making it get closer and closer to this plate. So a lot of this was like the last minute week and a half thing where we had to like make a change. So this just sits like this, and then it moves that nozzle. And the biggest thing from last year's group is that last year's group had a bunch of metal plates, and to change the height of the plate, they would open up the section, move the plate up, and then hand tighten it. So it wasn't very accurate. And so, but we're able to also, every time you have to like make a manual change, you have to open up this test section and then do the change and put it back. But then you have to depressurize it, which means you have to like pull all the air out of it, which takes like 45 minutes. So, you know, they took multiple days to do this testing, whereas because we were able to change the height of this plate from outside the test section, we could, spray the plate. Okay, we got that data, great, go to the next height. And we enter in a command on the computer, this goes up, and then we can just go on the next test instantly. So what they did in multiple days, we did in a matter of like 9 hours or so. So essentially the way this imaging works is you have a light source, right? And it's getting bounced. Basically, you put a mirror here, it gets bounced on this mirror. You put another mirror, it gets bounced there, and it's getting bounced all over the place, right? So eventually, the light gets bounced through here, like through this window we're working in. And that light then gets bounced into a camera. This camera is taking 200,000 frames per second. So like a 5-second video is like 8 gigabytes. So, and we had 27 of those videos. So basically, in a more generalized sense, the way this is working is that when you have air here, let's say you have air here. When you compact air and make it more tight, so they close together, it refracts light differently, so it looks different. And so basically what this is doing is these black lines are much more dense air packed together, and so they're making the light through it look different. That's why we're able to see, because before with the naked eye, you wouldn't be able to see any of this, right? But because we're shining this light through it, this camera is seeing this, and we're basically able to image all this. So this is like a GIF, but that's just like an example of like what the test looks like. The test was like, it was like a matter of not even like 2 seconds. It was like, and that's it. But so yeah, essentially. So that's like compressed air. You spray it onto the sensor, and then we get those values. So basically, the sensor is it's using a thing called a piezoelectric material. It's kind of cool. So you have a crystal inside, right? And that crystal can stress and strain and change shape. And when you do that, the reason why it's called a piezoelectric material is because when you stress or strain the material, it gives off a voltage. And so basically, by blasting this thing with air, we're vibrating it and like putting stress on it. And so it's constantly outputting voltage values. And then we're basically able to turn that voltage into a pressure. So we know what the pressure was.
I have a question.
Yeah.
Who designed your logo?
Michael
it looks
Abby.
beautiful.
Where's my A? Where's my A plus?
So,
where is it?
How pretty you are.
So this is really cool.
My daughter's hot.
Okay.
To put all of our electrical components all in the same place, basically this is what's called an Arduino. This is like the brains of what we're doing.
I thought you were the brains.
To a certain degree. So all of our electrical components get hooked up to this, and then this just gets plugged into a laptop via like USB, right? So we have, from one button press, we can press like fire, right? And what that's doing is it's sending a signal. This is called an oscilloscope. This is what allows us to record what that sensor is reading. So by pressing fire, this sends out a signal to the oscilloscope to tell it, hey, start recording. It sends out a signal to the camera we're using to get these to say, hey, start recording. And then it also sends a signal to the compressed air can that they have in the room saying, hey, start shooting. And so in one button press, it's all simultaneously starts shooting and recording at the same time. And then also from that same program that we made, you're able to change like the height. So you can press 1 for height adjustment or press 2 to fire. So we were able to do it all in one place. And putting all the electrical components on one board makes it easier because these are all like, these are soldered connections, right? So this stuff is connected. But then we put our own little razzle dazzle on it. So here's the old logo, right? Here's the name of the project. Here's all of our names. And then Jet, who made this, decided to put our Discord profile pictures on the back of it. So it's kind of a personal touch to it. In fact, we gave one of these to Rabinovich, one of our advisors, and he has it displaying in his office right now, which is kind of cool. A lot of this was like the last minute part, because as you can see, this was supposed to be a circle, but because we had this big thing inside the tunnel, like you can kind of even start to see it now, and you can't spin this because it's just going to hit this big like tube underneath here. So we had to like basically cut both sides of this plate off. So yeah, like the hole also, this plate was originally just a circle, and there really wasn't anything to it. So we also had to get the drawing of like, from the manufacturer of the sensor as to like, they tell you the dimensions of what the hole is supposed to be like. So now we machined this, now this thing just screws in from the bottom. So it's just there, and it's like flush with the surface, which is what we wanted.
I like your shoes, sir.
Oh, thank you, sir. Brand new, actually.
I like your tie.
And then, thank you. Blue and gold, it's a classic. This is the part that I printed that was scuffed, but then we brought it to the machine shop and we got it to work. Basically, if this pole wasn't here, this thing would just spin, right? The way this works is that, you have this screw basically, and this motor turns this screw. And so this then has threads in it, and it's able to move just up and down. But if this pin wasn't here, this thing would just spin like this. So we also had to put this in here so that this can just only go up and down. And then also this plate is all custom as well, because we had to get the whole dimensions of like this motor, put it in there. But then we also had to counterbore on the other side to be able to put a screw going through here so that we could attach this post. This is what's called an optical post. Basically, this little thing, you put it inside in the tunnel, and it just sits there. It's how you hold it up, basically. So A lot of this is like custom machining, like this stuff as well. There weren't holes in the plate to allow it to like spin, so we had to make all that. And then these are all like 3D printed parts underneath. So it's like a gym bench. That's what we kind of use the inspiration for, where it has these different holes, and you just put a pin through it, and then that's how it stays. And it's actually, the funny thing is, these screws aren't even like, the way it works is that these pins are, they're threaded at the start, but they're like clean, they're smooth on the inside to allow it to spin easily, but then it's threaded so that it locks into these posts. These aren't even screwed in all the way, but this thing is like rock solid, because as you can see in the video, this is the plate. Last year's group, it was like vibrating like crazy, right? So it was just like, the testing wasn't good because the whole thing was vibrating. This thing's not even screwed in all the way, and it wasn't moving at all. So the video stuff came out well. It's the pressure data that got scuffed, unfortunately, because that thing wasn't working correctly. You know, it is what it is. But yeah. So basically, you know,
You've been busy.
yeah, a little bit. This is like, so before we could test it in the tunnel, we had to show, for the sake of the project, that we could test it just like in the normal ambient air. So this is when we took just like this, we took a compressed air can and like basically squirted this thing. And I call it the hummingbird data because it looks like a hummingbird.
It does.
But,
Oh, yeah.
So basically, what this is doing, what this sensor is doing, is that it's not measuring just pressure. It's measuring a change in pressure. So. So basically, as it's increasing, that means that the pressure is increasing on the sensor. But there are points where that data starts to flatten out. That means it's no longer like detecting a change. So it's still getting sprayed, but it's no longer detecting a change. So it's returning like zero voltage. So that's what's called steady state. We want to see. Basically, what we want to see is that's called steady state, where it detects no change. We want to basically get information from like right before what's called the transient stage. That's where all of the interesting stuff happens. So that's what we're looking to do. But
Is that your teacher?
that's one of them, yeah.
Is that the one you want to speak to?
Yeah. Well, he's getting the spiel.
turbulent flow, right? Ridiculous.
No. That's Professor Alvin right there to the left. Remember that? And he just walks around. But like, that's that guy. It's so
Oh
funny.
my god.
Dude, he's the GOAT. I kind of want to say hi to him. I don't know where he went though.
Oh, it jiggles.
Well, Grant, very precise.
This is when I lost.
Our boy is smart.
Still ugly. Stinky too. Too bad he smells bad. Right now.
Hey, you two clowns together.
Yeah. Wait. Take it. Oh, I gotta keep the coach. Wait a minute. Wait. Let me get. Whoa. Hold on.
Will you two stop and smile for once?
Get your.
Which camera am I looking at?